And we will also have hands-on activities that will also be conducted by Maurício. So I hope you are enjoying the school so far. And just some regards, you can ask anytime you want. And for the ones that are watching this course online, you can send messages on YouTube or in the Google Meeting. We have eyes on both, and you can transmit your questions to the speakers. So, thank you.
Again to this week to the final lectures related to Monte Carlo event generators. As Matthew says, my name is Mauricio, and it's important to say again that you can send any question to that email that appear here. And after of start the 5 and 6 lectures, it's necessary to do a set of revisions of the concepts that we see during this week. So the title of the 5 and 6 lectures is related to the use of scripts for math graph and the data analysis of the events that we obtain using math graph. So I separate these 5 and 6 lectures in 3 parts. In the first part, we are going to remember some concepts that were important, and we are going to use to the analysis of the events that we are going to analyze using Python language. So it's important to review that concepts. And for the second part, we are going to review again the interface of the MATLAB interface, and we are going to show basic scripts that we can use to start MATLAB and do all the analysis and all the parameters necessary for the simulation. So we can use scripts for do that. And at the final part of the lectures, we are going to analyze the events, the histograms, and reproduce the results of this paper that appear here. I am going to comment some general results of this paper in that we analyze in a collider and a future collider that is CLIC. CLIC means compact linear collider, and the idea is see what is the luminosity that CLIC, the compact linear collider, need to find a new Z prime from these two models. The leptophilic Z prime model that I explained that is a model that in that we have a Z prime that only couples with leptons. That means leptophilic. And we have the popular model, 331 model with right-handed neutrinos and left-handed neutrinos. This was the objective of this paper, and we are going to show the process that we made to find the results. For example, here we have the two types of Feynman diagrams that we analyze in MATLAB. So we have the signal and background that are concepts that are very important. When we say background, we refer to all the process that only contain standard model particles. So we call that as background, okay? For example, if we have this type of diagram is a S channel, and this type of diagram is a T channel, okay? So when we have the photon gamma and Z here and here, we refer that are diagrams that are from the background, okay? Because Z and gamma are the bosons of the standard model. But when we use the Z prime, that is a beyond standard model particle, that is our objective of study of this article, of this paper, we call signal. Okay, so we have two types of events. Events related to signal, where we only have beyond the standard model particles, and interact with, depend on the model, interact with the standard model particles. But we have inside of the spectrum of the particle spectrum of the model, we have beyond the standard model particles. But when we only has standard model particles, we call that type of events background events. So this is important. So these are the two types of diagrams that we studied in this paper. We have here the comments about of the Lagrangian that were implemented using fine rules. We have here the Z prime interact with phi. Phi in this case are the fields related to the leptons, for example, in the case of the leptophilic Z prime model. And we can use the same Lagrangian to represent the interactions in the case of the 331 model, that is another model that has another types of interactions. Like, for example, we have interactions between quarks, up type quarks and down type quarks, and we have also interactions between leptons and the neutrinos associated to that leptons. And we see that the couplings are very, very different from the standard model couplings. So in the case of the leptophilic Z prime model, we have the same couplings of the standard model, but the difference that is we have a new Z prime that is heavy in that case of the leptophilic Z prime. And in the 331 models, we have another types of couplings, okay? And the objective of the paper is basically, if we are going to obtain that types of histograms in that appear the results, for example, PT is the transversal momentum. That was a variable that we study in the, I think that it was in the first lecture. And we have the eta, the pseudo rapidity, and we have the invariant mass of the particle of the final particles, the final electron-positron pairs. So our objective here is compare the data coming from the background and the data coming from the signal, and our objective is find the region inside of the detectors in that we can decrease the background events and increase the signal events. This is our objective when we analyze data from collider physics, searching in the sense when we are going to search for new physics. We find here, for example, if we have a mass of a Z prime coming from the, for example here, coming from the leptophilic Z prime model, if we have a mass of that value, we can find a new Z prime if we search events with that value of PT, or between -2 and 2 of pseudo rapidity, or in that region of invariant mass. So our algorithm search for that regions using an algorithm that we call random search. Okay. As a comment, that types of analysis we can use machine learning techniques specifically deep learning techniques, in that the machine learn what is a event coming from the background and an event coming from a signal and produce the same results. We use that metric that say the sigma, the significance, statistical significance. So we find, for example, that we have that value of luminosity. We can find different types of z primes mass for each one of the models. So basically, this was the research related to that paper, and I am going to show what is the process to obtain all that plots. Okay, so to do that, we start the second lecture in that we are going to remember some concepts related to the others previous lectures. So we start with that first part. We start, remember, an event in particle physics is any result of an interactions. In that case, imagine that we have only two protons, a beams of protons, because we use a package of protons. We don't use only proton and proton. We use a package of protons versus a package of protons. And before of the interactions, we only have protons, obviously. That protons can emit photons because are charged particles. We call that effect as initial state radiation. But in general point of view, we only have protons in the initial state. And by the quantum field theory rules, we have a set of new particles that appear after of the collisions. So that we have here in that case a set of events that can be electron-positron pairs, two photons, three photons, two jets, missing transverse energy that are related to neutrinos, for example, and that is the definition of events. Okay. And remember, we have the collider coordinates. That is important to say that is a choice that the particle physicists use to determine the directions of the beams. For example, the particles are accelerated in the directions of the z-axis. So the particles are accelerated in this case, in this scheme of the LHC, are in the z directions. Okay. And the x-axis, for example, point to the center of the LHC. So we use that type of collider coordinates, and we can say here, for example, the PT, the transversal momentum, that are the components in the transverse plane. In that case, the transverse plane is the x and y plane. Okay. So all the components of the linear momentum that that is in that plane, we call a transverse momentum. So we see that we can use the special relativity to write a different four vectors, position, velocity, acceleration, etc. And in that case, we have the most important four vector to analyze the events. That is the four momentum. The components for a particle, for example, this P is related to the proton. So the proton has an energy E in the first component, and the other three components are the components of the linear momentum, the components in X, Y, and Z. For example, in the case of the LHC, at a center of mass energy of 13 TeV, we have 6.5 TeV for each one of the protons, and we see a difference here in the Z component. We have a minus sign here because we know that are in opposite directions, and we don't have components in the X and Y components of the linear momentum. according to this choice of collider coordinates. So we have another important thing to say, that a proton is not a fundamental particle. It's a particle composed by another particles that we call partons. For example, the general point of view, a proton is made of three valence quarks. That is two up quarks and one down quark. For example, the diagram of the left-handed. But the modern point of view, this is a proton, in that we have the interactions between the three valence quarks, and we have the production of a sea of virtual particles that emerge from the vacuum according to the quantum field theory, and instantaneously is annihilated each other. So we have a set of particles that we call partons inside of the proton. That model is the parton model, and is applied to another types of composed particles that we call hadrons. Hadrons are mesons and baryons. That is the same definitions for example, of a meson that are made of two quarks, or a baryon that is made of three quarks, like the proton. Proton is a baryon. Okay, so we can write the with that p, we can write the four momentum of a proton. Okay, but exists an important comment here, that the nature of the proton, that we know inside of the proton we have partons. The partons charge a portion of the total forward momentum of the proton, given by this line of this equation. For example, if we have a parton 1, that parton charge a part of the energy and the linear momentum of the proton. Okay, and that x1 is given by is a randomly quantity that is given by a definition that we call parton distribution functions, that we saw that that quantity is inside of the integral of the quantum chromodynamics master formula. So we see also that produce a problem, because, for example, we can produce at the parton center of mass energy, we can produce, for example, a Z boson of the standard model at rest, by in our laboratory reference system, that Z boson can be accelerated. We call that boost. We produce a Z boosted. Okay, and in this center and the parton center of mass energy, that Z boson is at rest. So we have two different physical information. So we need to do using special relativity to transform and find quantities that has the same value in that two types of reference system. We use that matrix that is a longitudinal boost transformation, and if we apply that matrix in that vector, we obtain the transformation of the energy and the components of the linear momentum. And we can see here, we saw in the lectures, that we can obtain that the components, the transversal components, are invariant under longitudinal boost transformation. So we can use to define the transversal momentum, PT, that are made of the transversal components of the linear momentum. We show that we can use to define the azimuthal angle, and we can obtain another quantity that we use, that is the rapidity. But remember, the rapidity is not an invariant quantity. The difference between rapidity between two particles is an invariant quantity. We show that. And using that difference between rapidity and the difference between the azimuthal angle of two particles, we can define that another invariant quantity that we call R separation. That basically imagine that we have two electron positrons. So the R separation is basically a Euclidean separation. Okay, this is the physical interpretation of R separation. Another quantity is the pseudo rapidity that we can interpret it. This is not a kinematic variable. This is a geometrical variable because depend on the angle theta. So for example, if we have a value of eta equal to 2, we have that value for the theta angle. So this is important because the form in general of the detectors is a cylindrical form. Okay, so we know that the collisions occur at the z directions, so we can identify the directions of the result of the collisions using the pseudo rapidity because depend on the theta angle. So that variable is important to understand for collider physics. So another thing that is important to remember is the number of events that is defined as the basically I say that for me is the one of the most beautiful equation because we have the combination of the experimental particle physics and the theoretical particle physics. The experimental variable, we have the number of events, we have the efficiency and the luminosity, that are quantities that we measure in colliders, okay? And sigma, that is the cross section, is a quantity that we call, that we use the quantum field theory to do the calculation and obtain. That cross section is given by this equation that is very, very difficult to solve. We have here obviously the integral on the phase space. We have the probability distribution, or that we call Parton distribution function, and we have the cross section related only to the partons. So we need to solve that equation to obtain the cross section, and and with the multiplication between the efficiency and the luminosity, we obtain the number of events in that analysis. The good news is that that integral that we can represent by this, we can use Monte Carlo event generators that use the Monte Carlo integral, the Monte Carlo method that I explain in another lectures. So as I say, we have a set of reject events and accept events. So all these events are different events that has different values of energy and linear momentum that are compatible with the cross section. So we can say we can use the Monte Carlo event generator to solve the integral and store a set of events that are compatible with that cross section. So this is the objective of, in general, of the Monte Carlo event generators. So now it's important to see the following. We see that we have different commands to start. We have only command to start a MATLAB. That is the MATLAB interface, because we use MATLAB in the interface that was programming by the MATLAB team, and we can generate, for example, proton-proton producing an electron-positron pairs. Okay, we generate that events, display diagrams. We can see the different diagrams that appear in that collisions. We have obviously the partons inside of the proton. We have here in 1 and 2 we have the proton-proton, but proton are made of quarks. So we have here the charm anti-charm producing a photon and a photon producing an electron-positron pairs, for example. So we have a set of diagrams that depend directly with the model. When we start MATLAB, the models for default that MATLAB loading is SM, that is the standard model. Okay, so we use that output. For example, collider school. With that command, MATLAB generate the files necessary to do that integral and create that folder collider school. Okay, inside of collider school we have, for example, if we open index, that is HTML file, we have information about the diagrams and the processes, etc. But here it's important to review that folder cards, because here we have different cards that we need to modify to produce the collisions. For example, if in one card that appear here, we have the information about the collider. We have the number of events that, according to this lecture, is the number of random numbers that we use to solve the integral. So for now we are going to use 10,000, and we have, for example, here the types, the particle types that we have inside of the beams. We have 1 for proton, -1 for antiproton. We have 2 for a photon of the proton of ion collisions. We have 3 or -3 for electron-positron beam, and we have -4 or 4 for muon anti-muon beam. The color? The color? Let me see. Okay, so this is the number of random numbers, basically, or that is equivalent to the number of events. We have the types of the particles that are inside of the beams. In that case, we use proton-proton. So here appear appear 1 and 1, and we have the energy of the first beam that is equal to 6.5 tera electron volts. That are for example, the energy of the LHC. We have the PDF. This quantity, the PDF, is the parton distribution function that appear here in the integral. So exists a large set of parton distribution functions that the nuclear physicists use that experiment to calculate the result of the interactions between ions or between protons to do that, to find that distribution that we use inside of this integral. Okay, so in that case we are going to use that parton distribution function. We have another things that, for example, we have the minimum transversal momentum of the electron-positron pairs. In that case are 10 GeV. All the units that appear here are in GeV. So we can modify all these quantities. We have eta, that is pseudo rapidity for the rapidity for a pairs of charged leptons that we are going to measure between -2.5 and 2.5. So this rank card is important because we use to configure the experiment, basically, and the integral. And we have another important file that is the param carta, in that we has the information of the parameters of the model. In that case, we use the standard model, so we appear here the for example, the mass of the quarks, the mass of the Z boson that appear here, all in Jeff, the mass of the Higgs boson, etc. So we can modify. Obviously, this is the standard model of particle physics. We don't modify anything here. But if we charge another model, like the electrophilic model, we can modify, for example, the mass of the new Z prime or the couplings beyond the standard model. We can modify using param card data. And another important thing to see the distribution is modify the that card that is the media analysis 5, that is an alternative package inside of MathGraph that we can represent the distribution, the histograms. For example, we have here the PT, the transversal momentum of the positron, that we are going to use for 14 bins or 14 bar, okay? And we are going to plot between 0 and 500 GeV, for example. For example, the invariant mass appear here between 0 and 500. So we can to initial the simulation, we use launch with the same name folder, okay? So we start here and we can type 3, for example, to activate it or deactivate it. Media analysis, we are going to use media analysis and run the calculation. In that case, the integral that appear here is solved inside of MathGraph, so that takes time. Can be a lot of time or a short time, depend on the number of simulation, that is the number of random numbers, or the process, okay? So we obtain here the result of the simulation. Okay, when appear again, that means that the simulation was finished. So we have the result in the folder. Inside of the same folder, we have events, and in events we have different files. That tar file contains the events of the particles. For example, we can open, we have here that the information about each one of the events that are compatible with the cross section. We have here, for example, we have the energy of the particles, we have each one of the components of the linear momentum. Basically, it's the most important thing that we can interpret it from that data. But exists the program, that is media analysis, that do that work for us. So the result of media analysis appear here. For example, we have here the delta R separation. We have the distribution of that result. Remember, our process is proton-proton producing two pairs of an electron-positron pairs, okay? Here, for example, appear an excess of events in around of 100. That means that the Z boson was produced at resonant. So we can see interpreted that type of histograms, the simulations, okay? So this is the number of events that is that number that appear here, okay? and L is the integral luminosity that for default media analysis use inverse 10 inverse of Ferrington barons. Okay, we can change that for the, for example, for the luminosity of the LHC, or another luminosity, for example, for the run 3 of the compact linear collider, that is 5 inverse of Atto barons. Okay, we can modify that. So this is an alternative to analyze the distributions, but exists, that is the final part of the lecture 6 of the afternoon, that we can use Python to analyze the same histograms. And you know, Python is better in the sense that we can do it anything. So I like Python to do that type of analysis. Um, so exists an alternative to use MatGraph. This is the interface of MatGraph, but we can use scripts to do the same thing. We close MatGraph, and we have, for example, that script. That is a script of MatGraph. Here appear the same commands that we introduce in the MatGraph interface. For example, import model SM is the same command that we use inside of MatGraph. So the difference is that we create a text file that contains the instructions that we pass to MatGraph to do the simulations. For example, we have here again generate proton-proton producing an electron-positron pairs, and that hash means that this is a commentary, because MatGraph inside is a program that for create MatGraph, the MatGraph team use Python. So the algorithms and all the other things that use MatGraph are in Python language. So we use hash to do the comments. So I put here a comment that this is a process that we are going to use the LHC. We have here another comment for another example, in that we can use another model, import model leptophilic model, that we implement in another lecture. But it's comment, so MatGraph don't use that line. The same thing, this is a process that don't contain photon, Higgs, and Z boson. Remember, that slash represent that we are going to generate that process, but the process don't contain photon, Higgs boson, and Z prime. Why? Because the result of that process only contain the new Z prime boson. So we call that process as a signal process. And here, because we charge the standard model part, the standard model, we use generate proton proton produce an electron positron, and we don't put any consideration. So we call that process as a background process. So the folder output that we are going to use, that is the name, result for Collider School, and we use launch for initial the calculation in that folder. So we put here shower. Shower is important to understand. Shower, remember, is that is the hadron level, is a hadronic shower, in that in the final state we don't have partons, we have mesons and baryons. Okay, so to do that simulation, we put here, for example, Pythia 8, that that is the alternative package that MATLAB used to produce a hadronization. But for that example, we put off, and we are going to do the simulation of detector effects using another alternative. So for now, I put off here and analysis off again. But better I put here math maybe analysis 5. I put here the analysis using media analysis 5 to show the same distribution that we obtain using the MATLAB interface. So we use here the same number of events, the same energy collisions. We have the same Parton distribution function for the fall. We have the minimal transversal momentum. We have the pseudo rapidity that I remember that is 2.5 in the card of the that we see, and we have the type of the particles here is 1 because we are going to use protons, and that 2 we don't use because we use here background, and we don't has information about the mass of a new Z prime because we use the standard model of particle physics. So this is all, and the form in that we start that script, that is sample script, that txt is we write the same command to start MATLAB, but we inform the name of the script and we press enter, and MATLAB do the same calculations. So we don't need enter to the folders of that folder like cards, modify cards, because we use the script. Okay, so we are going to wait. And we can see, remember, that was the results using the MATLAB interface. Okay, for example, for the invariant mass of two pairs of electron positron pairs, we have that appear here, the zero in producing in a resonant form, etc. But we generate this folder that contain the same result. This is the other PDF that contain the result of the distributions, and we can see that has the same information basically. So we can use MATLAB. This is the message. We can use MATLAB using using the MATLAB interface, the interface of MATLAB, or using scripts. Okay. Now we are going to use again, because we see in that lecture 3 that we can produce events at Parton level, hadronic level, that appears mesons and baryons at the final state, for example, and we can put detector effects. Okay, so for example, we are going to do that, but in another configuration. We open that script, and we are going to use this standard model again, the same model. We are going to generate, in that case, that collisions that is different. Why electron-positron collisions? Because we are going to use another configuration for the collider. We are going to use the compact linear collider. So we maintain the same. No, we are going to modify here. Result for collider school and add click, for example. Click. Shower on, because if we are going to do simulations using detector level, we need in the final state hadrons. Okay, so we shower, we put here Pythia 8, okay, to do that shower. Detector off, analysis off, because the analysis we are going to do in the afternoon using Python. So for now, we put off in the analysis, and we have that number of events that for we are going to use that number for time, for time. The compact linear collider is a linear collider that works with 1.5 TeV of each one of the beams, of the electron positron beams. So we activated the parton distribution function of the electrons. Here appear a comment that means that the electron has partons. Click that PDF of click simulate the effects related to the emission of photons of the electrons or of the positrons. Okay, the electrons traveling to that energy are accelerated and can produce photons. So that PDF simulates photons. That no means that the electron has partons like quarks and gluons. That no means in that case. And we comment the PDF of the LHC. We are going to use the same minimal code of the transversal momentum. We are going to use, for example, 3.0 for the pseudo rapidity, and we comment the type of the particles, because 1 is for the proton, so we comment that. And we have here, we set the type of particles -3, because we have here positron, okay, and 3 here because we have here electron. So we change the particle type that we are going to use to the collisions. And we don't need that information about the mass of the Z prime and the width of the Z prime, because remember, that is the event, a process that are inside of the standard model, so we don't need information about that two parameters. So we are going to save that, and we need, no, this is all. So we generate again the same. Apparently all is okay. So we are going to start. Obviously errors can be appear, so we need to see again the correct script. Okay, we need a correct script. So here appear the calculation. Remember, inside of math graph we calculate that integral, and we simulate the initial state radiation and final state radiation of the electron-positron pairs, given by that parton distribution functions, or I prefer to say probability distribution functions. Okay. Let me see. I activated the shower, yes, with Pythia. So here is start Pythia, And Pythia takes all the Parton events and convert to hadron particles. So we can close here, and we have here the result, and here appear the events. We have two types of events here. We have unweighted events that are the events related to basically the events related to the partons at a parton level. But we have here the events that was hadronized. Okay, so we to put detector effects, we need to start, in that case, Delphis that we can install inside of MatGraph. Delphis, here I have a script for Delphis. Delphis is a script that is very basically, we are remove with that command, we remove that root file, that because that root file is the root file that was generated in another simulation. So for the, for evit errors, so we are going to eliminate that file. So we start that algorithm Delphis Happy MC2. That is an algorithm that takes the card of the experiment. In that case, click the the experiment has that card that contains the information of the this is the name, Delphis card click. Delphis card click contain the information of the experiment, the efficiency to detect muons, to detect electrons, etc. Detect information about the electromagnetic calorimeter, the hadronic calorimeter, etc. So we don't modify anything, any number that appear here, because this is a card given by the click collaboration. So it's a future collider, but exists a study that say we need to put, we expect to detect electrons in that region, etc. So all that information are inside of the Delphis card. So the script of Delphis use that we inform the folder that we find Delphis card that appear here. We are going to create a root file, and we are going to put the result in a folder that we are going to use that folder. Okay. And in that folder we find events. In that folder we have events, and events we have 101, 101, and we are take that file, but that file is only extract that is inside of that file. Okay, so we have that file. So that file, remember, that file are the events that were hadronized. So after of that, the types of events that we are going to use is LHCO files. That is another type of organize the information of the particle. So we are going to take that root file, and we are going to send the result to the same folder. And remember, we use the background detector effects click, for example. So we start that Delphis here. We start that simulation, that detector effects with that command, sh script, the same name that appear in that has that file. We start and that script simulate the detector effects in the click. We can use another types of configurations like Atlas, CMS, LHCb, NA64, etc. So we obtain the result in that folder that we inform events, and we obtain the LHCO file that contain the informations of pseudo rapidity, the azimuthal angle, the transverse momentum, etc., of the final hadrons that were detected by click. So this is the most advanced form to analyze events. Okay, we have here events that are hadrons that pass through the detectors of the click. Okay, and in the afternoon we are going to analyze that type files, and show the distributions inside of the click experiment. So this is all. Any question?
We are now open to questions.
You show the page of the LHC PDF or the PDF labels for everyone to see.
The
Because sometimes
paper?
no, not the website of the PDF label.
Ah,
I think
the
it's
citing.
important. Yes. I think
I show in another
oh, okay.
lecture.
I
But remember, if you need another Parton distribution function, you search lhpdf6, and you open that site, and you click here PDF sets, and you say that exists, but that is a problem of the page. But you can see that you have a large set of PDF that you can use. For example, if I do simulations in the future circular collider, we need an appropriate Parton distribution function for that type of energies, because the FCC works at, in the case of hadrons, 100 TeV. Okay, so we need a correct Parton distribution function for do the correct simulations. So that is the site in that we can find different and we have here the papers that, for example, that paper say what was the technique that the nuclear physicists used to calculate that distribution. Okay. And another question or
no,
comment?
yeah, only comment because sometimes depending of the analysis the people can analyze, it's necessary to use the same PDF.
Yes.
Because in the case you use other PDF, the results is very
Mhm.
different. Okay. The other comment is okay. In the case, for instance, Mauricio used Delphis to detector effects, but there are other packages. I don't know that you mentioned in the other.
Yes, I
lectures.
mentioned
Okay, it's on
Delphis is a fast detector. Basically,
yes.
that contains numbers that suppress the number of events, but exist. For example, was commented in the maps lectures that is better used. For example, Gian4, because in GM4 you define the longitudinal of the detector. You define the numbers of atoms, the configurations of the atoms that are made of the the detectors, the calorimeters, the gases, etc. So it's more advanced. It's a more advanced form to put detector effects in that types of events. Okay, but Delphis is a fast simulations, fast detector.
Yeah, fast detector, right. Sometimes, for instance, in the case you need to use other package, for instance, math analysis, right? Uh, you can obtain the output of PITIA in MATLAB, like Mauricio made now. In this case, you is the input file to math analysis, and math analysis can obtain the bounds and reinterpretation with other analysis in this package. Other important point is that statistics included in math analysis file, because you can make the likelihoods or other things and improve what is the best excluded region in your model, in your scenario. Only the
Yes, this that thing that you Shara mentioned is important because media analysis is a very powerful tool to do that type of analysis that works in advanced techniques using C++ language, a programming language. So it's important to understand that. And exists algorithms that are implemented inside of media analysis 5, and you can do it that type of analysis. Obviously, in Python, you can implement that type of statistical analysis and use another libraries that you can import to do analysis. You can use Keras, TensorFlow to implement deep learning algorithms to analyze that events, etc. So exist different alternative to do the simulations and the analysis. Okay.
So, any more questions? No? I think we can go to lunch then. Thank you. Let's thank the speaker one more time. Thank you, Maurício.
Thank you.